Okay, this is going to be the last part of the Chapter 6 videos. This is going to be looking at applications of logs and exponentials. So we're going to be looking at a little bit of finance with compound interest and continuously compounded interest, and then we'll also look at a couple examples of exponential growth and decay. So as a little bit of an introduction here, here's a formula for simple interest. That's I equals PRT. I is going to be the interest earned, or maybe the interest owned if it's a loan. P is going to be the principal. That's going to be the amount loaned or invested. R is the interest rate as a decimal, and then time is based on 1 year. So simple interest is going to be applied at the end of the loan or the end of the investment once, and that's it. If we're looking at compound interest, you're going to be earning interest at regular intervals. And so the big difference is not only are you going to be always earning interest on the principal, but you're going to be earning interest on top of your interest. And so it's going to compound on itself. So let's go ahead and get started and get into the compound interest formula. So we're going to look at compounded interest. And we're going to be earning interest on top of interest. The formula is A equals P and then times the quantity 1 plus R over N raised to the NT. So be careful, this exponent here is an N and then a T, not an R and a T, so be a little careful there. Okay. The A is going to be a money amount. That's going to be what we call the future value, or that's going to be the ending amount, or what you want in the future. P is going to be a dollar amount. That's going to be your present value, and that is your principal or your starting amount. Okay. R is going to be the interest rate as a decimal, so we do need to convert our interest rates into decimals, because that's what they mean. Percent means per 100, so that means you need to divide your percentages by 100 and then just drop the percent sign. Time is going to be in years for the compound interest, and then N is going to be the number of compounds per year. So commonly used compounds per year annually would be once a year. Biannually or semi-annually, that's going to be twice a year. So your N will be equal to 2. Quarterly will be 4 times a year, so your N will be equal to 4. Monthly, N is equal to 12. And then daily, N will be equal to 365. Some books might do it for use 360 instead. We're going to be using 365, and we won't worry about a leap year or something like that. Okay. And I guess I'm mentioning sometimes it's 360. Okay, but for us, we're going to only do 365. Okay. So we're going to do a number of examples. I do also have some separate videos where I solve for the principal, solve for the amount, so solve for present value, solve for the future value, solve for the interest rate, and solve for the time. Solving for the number of compounds is rather difficult. So there are some individual videos on those too if you want some more examples, but I'm going to do a couple examples with you guys. Probably not solving for the interest rate because we don't do that too often. Alright, so let's go ahead and look at the first problem here, and we'll go ahead and speed it up a little bit. Okay, so JJ invested $3,500 into an account earning 5.5% interest compounded quarterly. How much will JJ have in 7 years? So this is compound interest. And so we're going to write down all our variables, A, P, R, N, and T. Because it asks, the question asks how much will JJ have in 7 years, that's asking about the future value. That's our A, so that's our question mark. His present value is he's investing $3,500. The interest rate is 5.5%, so that means 5.5 per 100. So that is 0.055. The number of compounds per year is going to be 4 because it's compounded quarterly. And then the time is given as 7 years. So amount is equal to principal 1 plus r over n raised to the nt. So we got all our parts, 3,500. 1 plus 0.055 divided by 4 raised to the 4 times 7. If I'm going to put it into my calculator, I probably want to write it like this. So those parentheses are very important, and I also would like to go ahead and multiply 4 times 7 and make that a 28. Oftentimes what happens is, if we're not careful, we'll raise to the 4th power and then multiply by 7 instead of raising it to both the 4 times 7 power. Okay, since we're dealing with money and we're solving for the amount, which is going to be money, probably 2 decimal places is going to be appropriate here. So our amount, after we plug that in, is going to be $5,130.18. So that is the future value there of JJ's investment. All right, so that's the simplest one, finding the future value. We're going to go ahead and look at another one. So I'm gonna speed this up so we don't have to wait forever for it to write here. So this time, Laura would like to invest some money into an account earning 6% interest compounded monthly. If Laura would like to have $5,000 in 4 years, how much should she invest today? So again, this is compounded interest. So there's our future value, present value, interest rate, number of compounds, and the time. So she would like to invest some money now, so that's her present value. So the present value is what we're trying to find. Interest rate is given as 6%, so that's 0.06. Compounded monthly, so that's going to be 12 for the N. And let's see, she'd like to have $5,000, so that's going to be our future value of 5,000. And the number of years is going to be 4. So amount is equal to principal 1 plus r over n raised to the nt. And I'll go ahead and mention, maybe if you're looking at present value here for compounded interest, there is a separate formula for it, and we get it from dividing by the 1 plus r over n to the nt, so that would be in the denominator over here, and then we can write it with a negative exponent. I would suggest not worrying about remembering that formula also, and just remember this one here and then plug in the parts there. But if you're feeling confident with the material, you can use this too. Okay, A is 5,000. P is what we're trying to find. 1 plus 0.06 divided by 12 raised to the 12 times 4. Okay. So what we're going to go ahead and do is we're going to divide by this right here. So it's going to be 5,000 divided by 1 plus 0.06 divided by 12 raised to the 48th power. So here's how we might want to put it in our calculator, like this. Again, you want to make sure you multiply that exponent, those 2 exponents together right here. Be careful, because you could get the wrong answer there if you don't do that. Okay, so after we put that in our calculator, the present value rounded to 2 decimal places is $3,935.49. That's the present value that Laura should invest today, so that she will have $5,000 in 4 years. Okay, I think we're going to do one more of the compound interest here. Okay, so this time it says, how long would it take Chrissy to triple investment into, let me make sure I'm wording this. How long would it take Chrissy to triple an investment into an account earning 7.5% interest compounded annually? Okay, so future value, present value, interest rate, number of compounds, and time. So it does ask how long it would take, so that's asking for a time. Our interest rate is 0.075, and compounded annually is 1. Now the nice thing about this is doubling time, tripling time, quadrupling time with this setup, with this interest rate and that number of compounds. The tripling time in this case is independent of how much money we put in. So if we put in 10 cents, it's to take that the time it takes to triple that is going to be the same time it takes to triple $1 million. So we don't know exactly how much Chrissy is going to put in, so we're just going to say that her principal is the principal, and then her future value will be triple that, so 3p. And so we'll go ahead and install that into our formula and see what we got going on. So yeah, 3p equals p, 1 plus 0.075 over 1, and then raised to the 1 times t, okay? And so this is an exponential equation. Our variable is t, so the idea is to isolate the exponential, which is all of this. So you do see I am already dividing by p here. So I'm going to divide both sides by p. And oops, I guess I erased that on accident. So then we're left with 3 there. And so you see that the principal actually absorbs out. So that's why it doesn't matter what the amount we put in was. The tripling time, as long as it's not 0, the tripling time is going to be the same. Okay, and then 1 plus 0.075 over 1, we can simplify that down to 1.075 raised to the 1 times t, which is t. So we are trying to solve for an exponent, and so we want to use a logarithm and the power rule. So we've been using the natural log. So we're going to take the natural log of both sides. You can also use log base 10. Take the natural log of both sides. So the natural log of 3 is equal to, and we're going to use that power rule that brings down the t. So t natural log of 1.075. To free the t, we need to divide by the ln of 1.075. So it'll be the ln of 3 over the ln of 1.075. And so that is going to be approximately 15.191 years, and then you just need to look at what the question is asking in terms of how many decimal places. Okay, that's compounded interest. There's another type of compounded interest, and that is, let's speed it up, the continuously compounded interest. So if I see compounded interest in the problem, then I'm thinking either the previous formula we were just looking at or this one. How I know it's going to be this formula is because it has the word continuously. So if you see the word continuously, it is, I might refer to it as the PERT equation because you have that PE to the RT. So the players are all going to be essentially the same. So the amount is going to be equal to PE to the RT. E is going to be approximately 2.71. We don't want to use that. We want to use the E in your calculator, because if you use 2.71, you're introducing a lot of rounding. A is going to be your future value, so same as the other one. P is your present value or your principal. R is an interest rate as a decimal, and then time is in years. And actually, problems with continuously compounded interest are a little bit easier because we don't have to deal with the compounds, and especially if we're solving for time, the natural log and E are inverses of each other, so those will cancel out when we compose the natural log with E. So that's going to end up being nice, and it's also very nice when we're doing continuously, certainly continuously compounded interest, but also with the exponential growth and decay model. Okay, so let's go ahead and speed this up a little bit. So here we have Arasema invest $4,500 into an account, earning 6.2% interest compounded continuously. So you see the word continuously. So you're thinking A equals PE to the RT. How much does she have after 3 years? So we're going to handle this in the same way we've done the previous ones. We're going to write out all our variables, A, P, R, and T, and then we'll go back to the problem and we'll hunt down all the values that we know. So how much does she have after 3 years? That's what they're asking us to find, so we won't know the future value, or A. Okay, and time is given to us as 3 years. And the principal is she invests $4,500, and the interest rate is 0.062 as a decimal. So the amount is going to be equal to 4,500 e raised to the 0.062 times 3, and then I'll kind of write it how most calculators are going to do. So oftentimes e is going to give you a little caret like that. Sometimes it also gives you parentheses. If your calculator is a little bit more fancy, it'll actually kind of put you up in the box there. And if you're looking for the e on your calculator, usually it's the natural log, and then you have e to the x there, and you get to the e to the x using your secondary or shift or something like that. Okay, so make sure you have those parentheses in there, and then go ahead and plug it in, and we're going to round to 2 decimal places. So our future value is $5,419.90. Okay. Let's look at maybe one more, and then we'll run into a couple of exponential growth decay questions here. So again, we'll try to speed this up a little bit. So we got George's problem here. So what interest rate compounded continuously would George need to double his money in 3 years? So it does have the compounded continuously. So continuously is A equals PE to the RT. Your amount, we don't know. It's not given to us. Principal is also not given to us, so they don't give us any money values. R is what we're actually trying to solve for, and time is given us as 3 years. So R is what we're trying to solve for, so that's our question mark. Okay. Now this is kind of like the previous problem, where one of the previous problems where we're asked to find how long does it take for the money to triple. This is slightly different because they're asking us what interest rate. But if our principal is P, then the future value is going to be double that, or 2P. So 2P is equal to P, e to the R times 3. Now, I'll make a comment that solving for R and for T in the continuously compounded interest formula is going to be about the same. You're going to divide by the principal, and then you're going to take the natural log of both sides. So it is an exponential equation because we're solving for the variable r, which is in the exponent. So we would like to isolate e to the 3r and then take the natural log. So we'll divide by p, and you see that the principal divides out, so it didn't matter how much was invested. The double is independent of how much is put in, as long as it's non-zero. Okay, so 2 is equal to e to the 3r. We'll take the natural log, and so we'll have the natural log of 2, and this is especially nice because ln and e are inverses, so that will free the 3r, and then we'll divide by 3, and so our interest rate is going to be approximately, exactly as ln of 2 over 3, which is about 0.023105. So if we want to convert that into percentage, it'd be 23.105%. And then it depends on how many decimal places they're asking for in the problem. So we'll give it a couple decimal places. Okay, all right. So that's it. There's, I think, another video or two on my YouTube channel if you want to see some more examples of solving using with continuously compounded interest types of problems. So next thing we're going to look at is the exponential growth and decay model, and so I'm going to go ahead and write the PERT equation right here. Okay, so our exponential model for growth or decay is a sub t equals a naught. So a naught is the little 0 here, e to the kt. So it looks a lot like the PERT equation here. A sub t is the amount at a certain time t. A0 or a naught, that's the initial amount or your starting amount. K is a growth or decay constant. So it's kind of like your interest rate. but a lot of times we won't be converting it into a decimal unless they explicitly tell you, hey, this is a percentage. And actually the first problem we're going to do has a percentage, so we'll kind of do the same thing as we did with the exponential, with the continuously compounded interest. T is going to be time, and with the exponential growth and decay model, time doesn't have to be years. Often it is. It could be hours, minutes, centuries. Just depends on the problem. So we're going to look at a couple of examples, and so let's go try some of these out. So I'm going to speed it up, so it's going to take forever to write. Go a little bit further. Okay. Oops. All right. So this says the world population in 1987 was 5 billion, and the relative growth rate was estimated at 2% per year. So we actually do have a growth rate given to us as 2%, so we'll end up converting that into a decimal. Assuming the world population follows an exponential model, find the projected world population in 1995 according to this model, and I think the problem will ask us to round to 2 decimal places. So we're going to go ahead and write our exponential model, a sub t equals a naught e to the kt, and we're going to try to make this similar to the previous types of problems. So this one has a little bit different stuff going on. So 1987, that's going to be the kind of the start of this, so we're going to say time is equal to 0. Okay, so our A naught is going to be our what we're starting out with. So our initial amount in our world population is going to be 5 billion. We're going to use 5 to represent 5 billion. Okay. Your K is given to us. That's your growth rate as 2% or 0.02. Okay, and then they're asking us to find what's the world population in 1995. So from 1987 to 1995. That is 8 years. So that gives us a time of 8 years. And then we're finding a sub t, and or you can think of it as we're finding a sub 8 because we do have a particular value here. Okay. So we got all the parts there, so we're going to go ahead and plug it in and see what we got going on there. So a sub 8 is going to be equal to 5e to the 0.02 times 8. Okay, so then I would write this as 5e caret 0.02 times 8 if I were to put that in my calculator. Okay, so this one's pretty straightforward, and after I calculate that out, I get 5.87 billion as the world population in 1995, according to this model. If you do a Google search, it's actually pretty close. I can't remember exactly, but I think it was like 5.7 billion or something, the actual population, according to Google. So that seems to be fairly accurate here with this particular model. Okay, we're going to look at 2 more examples. Try to do a variety of different things that, or look at a variety of different questions they can ask us. So this was exponential growth. We'll look at another exponential growth with bacteria, and oftentimes they'll do exponential decay, and usually that's with some sort of radioactive substance. Okay, so we're going to go play with some bacteria now. Lots of bacteria. Okay. All right, so what do they want us to do here? So they say a bacteria culture starts with 900 bacteria and grows at a rate proportional to its size. So that means it's going to follow an exponential model. After 3 hours, there is 2,700 bacteria. So they just give us some information, and there's actually 3 parts to this. So we're going to look at part A. And part A is going to say, okay, so using this information, let's come up with a formula. Let's come up with a model here. Okay, and they might use the variable p. I think I might have the variable p in the notes. So the only thing different was we would do p sub t instead of a sub t. Other than being a different variable, is no different. Okay, so let's go ahead and extract some information. So we do start out with 900 bacteria. So that's our initial amount. Okay. Our K is, it says it's proportional to its size, grows at a rate, but doesn't explicitly tell us what that is. So We don't know what that is. However, we're given some more information. So the time at 3 hours, so the time at 3 hours, they tell us that we have 2,700 bacteria. So we actually have 3 out of the 4 variables, so we're going to end up solving for K there, and that's going to give us our model. Okay, so A sub T is equal to A naught e to the KT. So our A sub T will be specific. It'll be A sub 3, which is going to be 2,700. And that's going to be equal to A naught, which is 900. E to the K times 3. Okay. This is an exponential equation because we're going to end up solving for K, which means that we need to isolate the exponential expression. So we're going to divide both sides by 900. So we divide both sides by 900. And we have 3 is equal to e to the 3k. Okay, to undo the exponential here, we're going to go ahead and take the natural log. And natural log and e are inverses, so that's actually going to free the 3k. The ln and e are going to undo each other, so they're going to go away. So we're going to have the natural log of 3 is equal to 3k. Okay, and then we're going to divide by 3, and so then we have our growth constant of ln of 3 over 3 is equal to k. And I want to leave it like that. I don't want to convert it into a decimal, because if I convert it into a decimal, then there's going to be some rounding. And if I do any sort of rounding intermediate to the process of solving this, that's going to introduce error, and so we don't want to do any rounding until the end of the problem. Okay, so let's put that all together as our model. So A of t will be equal to the initial amount, 900, e, and then our k is ln of 3 over 3 times t. Okay, and so now we can use this to answer a variety of different, well, there's really 2 types of questions. The 2 types of questions are, how many bacteria do I have in a certain number of hours, or how long will it take for our population to reach a certain number of bacteria? Those are the 2 questions we can really ask. So we're going to look at an example of one of each. So here's our model again, so we have it in front of us. And the simplest part, once we got our simpler of the 2 questions, is once you got your model, they'll ask us like, what will the, how much bacteria, or what's the population of the bacteria after, 8 hours. Okay, so all we got to do is plug 8 into the formula. So here it is. I'll go ahead and write it how you would most likely write it in your calculator. It would be 900 e caret parentheses ln of 3, close the parentheses, times divided by 3, and then times 8, close your parentheses. Okay? And since we're talking about bacteria, I don't want fractions of bacteria, so I think what we're going to end up doing is we're just going to round up. Okay, we'll round up. So I'll get 16,847 and some change, so we'll round up to the next whole bacteria. Because I don't want fractions of bacteria or decimals of bacteria floating around here. Okay, so that's the easier type once you have your model. The second type is a little bit more complicated because we have to do a little bit more in terms to solve it, and that's solving for how long it takes the population to get to a certain value. Okay, so we'll go ahead and write our model again, and this time the question is when will the population reach 1930 or 1,930 bacteria, and then they'll want us to round to 2 decimals is I think what they're asking online. Okay, so that A of t, so you have 2 variables in your formula, A of t and t. So A of t is your population, t is your time. 1930 is not a time here; it's a bacteria. Okay, so we'll have 1930 as your A sub t equals 900 e to the ln of 3 over 3 times t. We are solving for an exponent here, so that's an exponential equation. So we want to isolate the exponential there. So that requires us to divide by 900. And we'll reduce to 193 over 90. That's going to be equal to e to the ln of 3 over 3 times t. To undo the exponential, or to get the exponent down, we're going to take the natural log of both sides. And because we're dealing with e, that's very nice, e and ln will undo each other. So we'll have the ln of 193 over 90, and that's going to be equal to the ln of 3 over 3 times t. So you have two choices here. You can divide by the natural log of 3 over 3 on both sides to free the t, or we can multiply by the reciprocal. That will have the same effect. So I'm going to go ahead and multiply both sides by the reciprocal. Okay, so when I multiply both sides by the reciprocal, you'll have 3 over 3, which absorbs, ln of 3 over ln of 3 absorbs, and so now the t is free. So we have the 3 ln of 193 over 90, and then that's all over the ln of 3. That's equal to t. And if we throw this into our calculator, we get approximately 2.08 hours. In the calculator, this would be 3 ln parentheses 193 divided by 90, close parentheses, divided by the ln of, ooh, that's not right. What should that be on the bottom? It shouldn't be a 90. My computation is correct, but I wrote down the wrong number. That should be a, what should that be? That should be a 3. That should be a 3 there. Okay. Sometimes we get carried away in the excitement and write down the wrong numbers. Okay. So that looks all right. The number was correct. The 2.08 was correct. I calculated it beforehand with the correct value in the denominator. Okay. All right. So we have one more example, and we're going to get into a radioactive problem, and then we'll also talk a little bit about something called the half-life. Okay. So I think we have a whole bunch of stuff to write down here. Okay. All right, so it says an unknown radioactive substance decays into non-radioactive substances. In 180 days, the radioactivity of the sample decreases by 33%, or we've lost 33% of the radioactive substance. So the first question here is, what is the half-life of the element? And we're going to assume that, or the substance in this case, and we're going to go ahead and assume that this follows our exponential growth and decay model. So they're asking for the half-life, and we need our model in this case to even answer that question. So we'll go ahead and come up with our model before we can even address the half-life question. So we're going to come up with our model first. So here it is generically, and then we're going to go see what kind of information that we have. Okay, so at the beginning we're going to have 100% of whatever it is, so you can think of that as 1 A naught, okay? And it actually doesn't matter how much of the substance that we have, but we'll go ahead and say we have 1 A naught, or that's 100% of A naught there. Okay. What else we got going? K, we don't know that. Time, they do give us some information, so they say in 180 days it decreases by 33%. So if it decreases by 33%, that means we have 67% of the original A naught left over. Or we can take 100% minus 33% for that decreasing, and so we have that 0.67 there. All right, so we got all that information, so we're going to plug in 0.67 A naught is equal to 1 A naught, e to the, we don't know what k is, and then times 180. Okay. So we're going to isolate the exponential because we're, again, solving for the k. We've got to isolate the exponential. So we're going to end up dividing by 1 A naught, so the initial amount didn't really matter, but we're just being a little careful. So we're going to divide by 1 A naught. And so we have 0.67 is equal to e to the 100k. And then we're going to take the natural log, and the e and the ln will undo each other. So we have the ln of 0.67 is equal to 180k. And we'll divide both sides by k, not k. We'll divide both sides by 180, pardon me. ln of 0.67 over 180. That's going to be equal to our k. Okay, so now we have our model because we have our initial amount of 1A naught, and we have our k, so we're getting closer to actually answering this question about the half-life. So a sub t is equal to A naught, or 1A naught, e to the ln of 0.67 over, oops, and I've written down the wrong value. Let me fix that. Sorry about that. 0.67. I wanted to write down 63 a couple of times when I was working this out, so we'll have to pay attention, make sure I didn't do it anywhere else. So ln of 0.67 over 180 times t. And so let's talk about the half-life. And so the half-life is the time required for half of a substance, whatever it is, to decay or to go away. So how long does it take for half of the substance to decay? Which means we have 50% of it left. Okay. All right, so if we have 50% left, our original amount was A naught, so half of that would be 0.5 A naught. That's going to be equal to A naught. Well, first we're going to call this the a sub t here, and then we'll set it into the equation there. So that is our amount here, and then we're going to try to find what the time is. And that time will be our half-life. So 0.5 A naught is equal to A naught e to the ln of 0.67. Okay, so looks like I put 0.63 on accident. So 0.67 over 180 times t. All right, so this is an exponential equation because we're solving for t and it's in the exponent, so we want to isolate that exponential. So we're going to divide by A naught. So we have 0.5 equals e to the ln of 0.67 over 180t. And we're going to take the natural log to make the e go away. So we have the ln of 0.5 is equal to the ln of 0.67 times t. Okay, and we're going to do the same thing we did before. We're going to multiply by the reciprocal, so 180 over the ln of 0.67, 180 over the ln of 0.67. Okay. So t will be approximately, well, here's our exact value. ln 180 ln of 0.5 over the ln of 0.67. Okay. After plugging that into our calculator, that is about 311 about 312 days. I guess we'll give it 2 decimal places depending on what the problem's asking for. Okay. So that's the half-life. So about 312 days, that's how long it takes for half of the substance to decay. So here I'll set up a little table here. So if we start out at the beginning, we have 100%, or 1. After 180 days, we have 67%. And then after 360 days, we're going to have 67% of 67%. So that's 0.67 times 0.67, which is about 45% about. The half-life was about 312, and that's when we have 50% left. So this seems to be consistent with what we got going on here. So we start with 100%. This information was given to us. And so if we go another 180 days, we'll have 67% of 67%, which is about 45. And you see the half-life, or 50%, falls in between the two there. and 312 is closer to 360, and the 50% is closer to the 45%. So that all seems reasonable to me here. Okay, so we had one other question we wanted to do here now that we have our new shiny model here. I don't know if it's shiny, but we have our model here. Okay, so how long will it take for a sample of 100 milligrams to decay to 51 milligrams? Okay, so that's really close to half. Half is left. So I'm going to guess it's somewhere around 312. Okay, so our A of t is going to be our future value of 51 milligrams. Our initial amount is 100. Time is what we're trying to find, and the K we found already. That's the ln of 0.67 over 180. So plugging it in, 51 equals 100 e to the ln of 0.67 all over 180 times t. And again, we're solving for an x. Oops, I don't want to do that with the eraser, do I? Not really. So I want to solve for a variable here in the exponent, so we need to isolate the exponential equation. So we're going to divide by 100. So we have 0.51 is equal to e to the ln of 0.67 over 180 times t. We're going to go ahead and take the natural log of both sides. We've done this like a million times now. E and the ln will absorb, and so we have the ln of 0.51 is equal to the ln of 0.67 over 180 times t. We'll go ahead and multiply that by that reciprocal again. So there we are, multiplying by that reciprocal. All right, so what do we got going? We got the time is approximately, I keep doing this. So exactly is 180 ln of 0.51 over the ln of 0.67. And now that's approximately 302, about 303 days. Which is pretty close to 312 days, so that seems reasonable. So anyways, if you're looking for more examples, I think I do have a little bit more example videos of exponential growth, decay, and then also the financial stuff, compounded interest, continuous compounded interest. All right, so I think we're done for today, so we'll see you next time.